Yeah, and then my other one pushed back, so everything happened. Yeah, but I don't know, the first one says.
And then same time, she's like, I thought she was at the dollars. I'm like, oh, great.
And then she was like, I was in there.
All right, how y'all doing? Everybody good? You look at any of those questions that we put up? Have any questions on those? Are you keeping up? No questions on the homework from last time? Or the practice stuff? Are you doing these? I lose eye contact when I ask that. It's your grade, so I, of course, suggest keeping up. You're gonna come back from spring break not remembering a thing that happened in this class for the last 2 months, so just make sure you're up on what we're doing this week. Well, this week and last week, but we're really hitting the sort of core of chemistry, chemical reactions in this chapter. So we did a bunch of numerical stuff, and then we talked about, here's the periodic table and here's atoms. Then we talked about 2 different types of compounds, ionic compounds, and that was test 1, and then we started the covalent compounds, and now we're going to talk about chemical reactions. Those of you who took chemistry before, you remember the word mole? Do you remember what it is? Okay, that's where I'm starting today. So the mole in chemical reactions is really hitting the core of chemistry. So if you've been tuning out since I started chapter 2, start tuning back in for this. So chapter 4 was the first chapter that would be on test 2. Chapter 5 is chemical reactions, and I'm really starting in 5.5. I'll do 5.5 and 5.6 first. I really feel like they went out of order here. So I'm skipping up to that, but mole is where we are. That's where what I'm getting at. I have this that I'll upload my awesome PowerPoint on the mole. I guess that's good for the camera. It is recording. All right. I made this a few years ago, and I think I went overboard on transitions and stuff. So I'll just leave it kind of open like this as I go. You see here where it says AMU, and here it says grams per mole. You only really need to think in terms of grams per mole. This chapter goes over AMU, but I'll go back to it if we need it, but I'll show you that those are kind of, numerically they're interchangeable. So these are things we'll talk about. I'm going to explain what the mole is. We've talked about grams before. This is going to be more useful. Grams per mole. And too many transitions. So let me start like this. I call these counting units, dozen. So you already know dozen means 12. Pair means 2. Maybe you've heard of score. Score means 20. Those I'm calling counting units. Let me get to the first problem here. So, and like before, like in the numerical part of things at the beginning of the semester, you had that chart that had all the conversions in it, metric to metric, English to English. Well, here's another one that you could write. 1 dozen equals 12. But of course, the way you're going to use that in a calculation is the way I've got written down low, 12 over 1 dozen. But notice, okay, 12 over 1 dozen, but let's say I'm actually talking about marbles here. So now I've got a label. And as is typical, I've got numerical value first, the unit next, and the label last. So marbles is our label because that's what we're talking about. But what I really want to point out here is let me put it like this, let's say there were 18 cars in the parking lot out there, and I said, hey, go out there and count the cars in the parking lot, come tell me how many there are. You're gonna come back and tell me 18, because of the way I phrased it. I didn't say, go out there and count how many dozen cars are out in the parking lot. Then you come back and say 1.5, because 18 is 1.5 dozen. What I mean is, after all this talk about units this semester, that way you learned to count when you were a little kid. 1, 2, 3, 4. Also called the integers, also sometimes called the natural numbers or the positive integers, those. When you're using those, there's no unit. That's this definition I have written here of dozen, using marbles as the example, is written correctly. There's actually a blank there where usually there would be units. Do you see what I'm saying? That's useful to know for when you're dealing with the mole, because that's one of the things that trips people up with the mole. But just as an example, I have 1.5 dozen marbles. How many marbles do I have? All right. If you look at this, look at the top sentence. I have 1.5 dozen marbles. You have there, within the question, the thing you're going to write down, a piece of information that you're being given. That piece of information is going to be in the formula you're going to use to calculate something. And notice it has a numerical value, a unit, and a label. And that's what I've got written down there over 1. And then the second part there, I put on the right side of the equal sign because that's where the question mark is. In fact, it says how many. So where it says how many, I put numerical value. I'm just representing it as a what do you call that? Numbers symbol, a hashtag. And then it says how many marbles. Notice there's no unit. It says how many marbles. It doesn't say how many grams of marbles, how many milliliters of marbles, how many scores of marbles. It doesn't say anything. It just skips the unit and goes straight to the label. That's what I'm telling you to look for. So that's written correctly. There's actually a space there between the number and the label. Usually the way you would write this is you wouldn't leave that space there. You would close the space. But I'm going to leave it there just to emphasize that there is something missing here, and that's proper because it's asking you how many marbles. The counting units, I mean the counting numbers, the integers. There's no unit there. And now I'm going to grab the definition of dozen from the other slide. Dozen. That's not in this question, but just assume you had that on a piece of paper somewhere. And notice I'm lining up. When we do this, you're either going to put 12 marbles on top and 1 dozen marbles on the bottom, or you're going to do it the other way around. You'll have 1 dozen marbles on top and 12 marbles on bottom. It just depends on what you're calculating. Here, we're given dozen marbles, and we're trying to calculate number of marbles. So I've got dozen on the bottom, so it'll cancel, and actually what it cancels down to is the blank. The blank is what's left, because that's what was asked for. It says how many marbles, question mark. So the blank needs to not cancel, and the dozen needs to cancel. You see what I'm saying? You with me? Too many transitions here. I just go ahead and finish the calculation here. But 1.5 times 12 gives you 18. Yeah, that's the answer. 18 marbles is the answer. This is asked slightly differently. So the piece of information that's on the left side of the equation that is a piece of information you're using to calculate. If I have 32 marbles, notice there's no unit. That's what I'm going to write, 32 marbles. And yeah, I put it over 1. I always put it over 1 just because it makes things symmetrical. And then on the right side of the equal sign, now I've got how many, that is number sign, dozen marbles. So you can set that much up and then go get your definition of dozen and stick that in. And of course, I'm not going to use it like that this time. I'm going to use it flipped over. Now the blank space cancels. You are literally canceling blank marbles with blank marbles. You see that? So leaving the space helps you see that this is when you're talking about absolute numbers, integers, counting the way you would count on your fingers. And yeah, if you finish this out, it's 32 divided by 12. two significant figures. This is a little weird because these are all exact, but I would still do this in two significant figures. But that's only weird for the example with marbles. Okay, so there's that. All right, now I'm gonna start over that sequence I just went through, but now I'm gonna use the mole. The mole is just another counting number. It's exactly like dozen, it's exactly like pair, it's exactly like score. The only thing that makes it difficult is it's a gigantic number. That's an enormous number. But we do that because, for instance, because when we deal with atoms and molecules, they're so tiny, to get just like a little pile of carbon atoms on my palm, that's about that many atoms. So we use that unit in chemistry. They use it in astronomy too to count stars, because there's that many freaking stars up there to deal with. If you had to count number of grains of sand on a beach, you'd want to use this. You wouldn't want to use dozen, that's not going to help you much. So that's why we use this, the mole. But of course, the other thing that makes this difficult, like dozen, the other thing that makes this difficult is we always use scientific notation for this because it's such a huge number. So now we have that power of 10. We're dealing in, we almost always write that number as 6.022 times 10 to the 23rd. We do know more digits out, they're not really zeros all the way out, but since you have to pick your whatever precision you're going to use the number to, I think that your book does 6.02 instead of 6.022, but it's like 6.0221314 something, I don't remember, but we do actually have this defined out. Human beings have this defined out to more precision, so. But so we got that power of 10 we're going to have to deal with. But now, I've gone through and fixed this so many times and it doesn't save it. But I guess I'll just do this as we go. I did it again just before class. So that's like the definition of a dozen, except I'm doing definition of them all. This is all of this in the top is the numerical value. It's just like what I put here. Might not be worth going back. That. Before I said we're doing marbles, I said it's 12 and 1 dozen. 12, there's no unit, so it's just 12 in the definition. And that's what I have down here. I'm actually going to have to fix those powers all the way through here. So that. Remember, the power of 10 goes with the numerical value. So you have numerical value, the actual value of a mole, over 1 mole, definition of a mole. All right. And I'll use marbles as the example again. I'm gonna have to fix those all the way through here. So this is just like that page where I had 12 marbles over 1 dozen marbles. But now it's this giant number of marbles over 1 mole of marbles. So it's already looking difficult because this just makes it look even more difficult, but yeah. Emphasizing the same thing here. There's a blank. You see what I'm saying? This whole thing is a numerical value. I got ahead of myself there. You with me? That's just like the same thing I had for dozen earlier. It's the numerical value that's very ugly to look at and intimidating to use in a calculation. Blank marbles is 1 mole of marbles. All right, so if I have 1.5 moles of marbles, how many marbles do I have? Okay, so I'm back to this. Information you're given, moles is the unit. We use MOL for the abbreviation. So you got your numerical value, your unit, that is a counting unit, in marbles. How many marbles do I have? that says how many marbles, there's no unit. So that's what you would write. And now you know how to use that definition I had on the other page. Gotta fix this. This is literally just the definition of a mole, this right here. And I've implemented it such that mole is on the bottom, so moles cancel, and you get blank, and you're literally gonna get just the numerical value of how many marbles there are. Integer, it is an integer. 6.022 times 10 to the 23 is an integer. As crazy as that sounds. The way I did the math here, yeah, that works out the way it is. I'll probably model calculating some of these, but let me get through this presentation. And then I did it again. Marbles. Too many transitions. I don't know why I'm doing this because it's not going to save those as like it should. But moles of marbles cancels, you get blank marbles. I'm just belaboring the point now. So now I'm doing it the other way around where you get it's going to bug me if I don't fix these. So 3.2 times 10 to the 25 marbles, there's no unit, so you write that down. And then you're asked for how many moles of marbles, so you put # moles marbles. Yeah, you flip it. Instead of using it like I used it before. I'll save this and upload, but realize it's not going to save me putting these into superscripts. It just never does. I don't know why. One more slide down, flip it over. So there, so now I'm lining up blank marbles with blank marbles. Again, definition of the mole. So on the bottom is where the blank is, and I have blank here because there was a blank here. So that's how you calculate this. Yeah, let me make sure I've got space. Just to give you because I don't do it on it on this slide really the way I do it. If I did it on a piece of paper, if I had this all set up at 3.2 times 10 to the 25 blank. So one, just a one. 10 to the 25 blank. I'm just going to say MAR, so I can save a little space. And then 1 mole is 6.022 times 10 to the 23 marbles. just to show you how they work with the exponents. It's 10 to 25 space marbles over 1. Space. Still don't have all the space I wish I had, but oh, yeah, dude. Like I've showed you before how I separate numerical values into units. If there's powers of 10, especially when there's more than one, I make 3 categories. So I'm gonna go 3.2, 10 to the 25th, marbles, 1 mole, what am I doing? Yeah, no units, okay. Marbles, blank marbles, and then moles of marbles, and then marbles. So the unit goes with the label. So this is blank marbles, this is moles of marbles, this is blank marbles. So I have blank marbles, moles of marbles, and marbles. And then I have 3.2 and 1. And down here I have 1 and 6.022. And this is what I'm saying. I put one more category here where I put the powers of 10. So I've just rearranged everything. Do I have everything over there? Got 3.2 and the 1 and the 6.022, 10 to the 25, 10 to the 23, blank marbles, moles of marbles, blank marbles. So blank marbles cancels. So I'll end in moles of marbles. This I would do with my calculator. Two divided by 6.022. Two significant figures, so I'm going to stop there. My calculator has 138, whatever, but I'm going to stop there. And dealing with powers of 10, you just take what's on the bottom, move it up to the top, and change this sign. So I have 10 to the 25 times 10 to the negative 23. I could say over 1, but once you put it all on top, you can just do it like that. And then, of course, it's just arithmetic from there. 25 minus 23. So I'm left with 10 to the 2. 0.53, 10 to the 2. Times 10 to the 2. If you're not asked to put it in scientific notation, you can leave it like that. Or standard scientific notation. I don't remember what I did here. Yeah, so I'm here. Back to the camera. Fix the camera. So if I wanted to put this in scientific notation, I want to move forward 1. So it's an answer. So I just do it in the slide. I don't necessarily do it the way I would do it on a piece of paper in the slide. But I'm really emphasizing that when you've got a power of 10 or more than one power of 10, I put all the numerical values here, but the powers of 10 are numerical values, but I put them together here and the units here, and then I work them all separately. I do that in the calculator. That I just do with the rules of exponents, and those just cancel. Focus back over here. Anyway, so paying attention to that blank where there would sometimes be a unit, but there's not a unit when you're doing, when you're literally counting numbers of things, is what I was wanting to point out. Before I continue this, go back here. I didn't find a lot of good examples in the chapter, but let me take us to into the chapter problems for something to practice. This is 5.65 and 5.66. Um, 5.66 is the one I'll do because I think it's the odd ones that you're given answers to. But I have a little bank of questions in the quizzes on D2L. So you don't really have to do that one, I don't think. But I want to rephrase this just to make it clear. How many moles of... Now we're talking about a molecule. And I hadn't done that yet, I just talked about atoms. No, I didn't even talk about atoms, I talked about marbles. But the antidepressant fluoxetine is a molecule, just like I was talking about last chapter. It is one individual thing that's just a very big molecule. So I'm not going to draw a molecule. In fact, they screwed this question all up. They didn't do subscripts. That should say C17H18. This isn't the important part though. F3NO. Okay, all of those atoms connected together in one big thing, but think of it as a marble. And let me phrase this. How many moles? And I won't use the word fluoxetine, I'll just write this, H18. How many moles of these, and I have to phrase this, are in I phrase it like this, maybe it'll help. So this is a molecule. That's the molecule. And yeah, they messed up this, they did a superscript here. You see that? I don't know, but those should be superscripts, not subscripts. Okay. Now let's do what we did before. Here's what you're given. You're given this, and this is what you're being asked for. How many moles of this? So I would do this. How many moles, and this is the label, C17H18. Given this many molecules of this, molecule sounds like a unit here. Let's say, I could say C17, this should help, C17H18F3NO molecules. Maybe I should be saying fluoxetine. So you would do this. More space. H18. Still need more space. Number of moles. But I'm emphasizing that there's a space here. This is an absolute number of these molecules, like counting on your fingers, like integers. And it's asking us how many moles is that? So when there's this space here, that's when you're going to use so 1 mole is this, and I have this flipped over from the way I had it in the slide, but it's the numerical value blank is 1 mole. Here's the blank, and the mole is over here, so I want mole up here and blank down here. Blank. What makes this seem tedious is this formula, but if I have this many of these molecules, how many moles do I have of these molecules? So if I rephrase it like that, maybe it helps, because they have that as A, B, C, and D. I did that a little clumsily, but do you see how I have this set up? So the phrasing in these types of questions aren't always as clear as you wish they were, but it's saying, essentially it's saying, I have this many of these molecules, not this many moles, not this many dozen, not this many grams, I have this many of these molecules. How many moles is that? So to solve it, I would put 5.00, got a 1 there. And on the bottom, I have a 1, 6.022. And then in the powers of 10 category, I have 10 to the 19, 10 to the 23. And all that's left are the units. You have blank these molecules, blank these molecules. We'll be left with moles of these molecules, but that's really kind of a double check because we knew that was going to be that. So this needs to end in moles. C17, H18, F3, divided by 6.022. So this numerical value is 0.83. I have more digits on my calculator, but that's rounded correctly. 3 significant figures, 4 significant figures. I want to have 3. 10 to the 19 times 10 to the 23. We need 10 to the 19 minus 23 moles. Get tired of writing this molecule. C17, H18, F3. What's 19 minus 23? That's actually the correct answer. It's just not in standard scientific. If I move the decimal up so it's in standard, that would be the answer. I know that's tedious. It's the power of 10 that makes it so tedious compared to the other calculations I'll do. I should do more of these. Let's look real quick at the ones I picked out for quizzes for you. Because I think those are phrased a little better. Man, it's hot in here. Still going. I need to take the first one out of here. Let me do that first before I forget. All right. Just tell me if this wording is better than what that one at the back of the chapter we just did. How many carbon atoms are in 3.85 moles of carbon atoms? So how many carbon atoms is the label? It says how many. So that's your clue that on the right side of the equal side it's going to have that blank. You'll have £, blank, carbon atoms in parentheses or in quotes. And then on the left side, you'll have 3.85 moles of carbon atoms over 1, and then definition of a mole to do the calculation. You see that? How many iron atoms? All right, and this one says a beaker contains this many zinc atoms. How many moles is this? So now on the left side of the equal sign, you're gonna have the blank. You have 1.5 times 10 to the 23 blank zinc atoms. Then definition of a mole. And then on the right side of the equal side, you'll have pound sign, moles, zinc atoms. You see into this? I can write some of these down, I just want you to have them as practice. All right, so practice these. There's only a few of them, but I've separated them from the ones that will, so I put all of those types together where you're using counting integers, and there's a blank. They're all there under the mole. So now I'm going to go back here. Continue with this. So I overdid these transitions too. So there's carbon, it says 12.011. You see this 12.011 here? And here's the periodic table y'all will have, so when y'all have a copy of. This says 12.01, so all of these on here only go out to two decimal places. For some reason, a couple years ago, I used a periodic table that had one more digit out, so don't let that confuse you. But here's the periodic table you'll have for the test and for your homework. And these numbers, the 16 there for oxygen, here's the way to think of that. The number you see there for oxygen this next section of calculations I'm going through are not going to have that 6.022 times 10 to the 23rd number in it. It's not even going to show up. Oxygen, let's do nitrogen, 14.01. You see 14.01 on the periodic table. That means grams per mole. And the unit mole shows up, but that 6.022 is not going to show up in anything we're about to do. It's kind of boiled in already, so to speak. You can write it this way, but of course, I always tell you guys to do this. So you're ready to do calculations. And this is for nitrogen. Instead of writing out nitrogen atoms, I'm just going to put the symbol in. That's what that means, what you see on the periodic table. That's how you're going to want to use it. 14.01 grams is 1 mole of nitrogen. If I went up to one of the scales in the lab and I somehow could have some pure nitrogen in my hand, which I can't, but pretend I could, I started sprinkling it on the scale and I put a little more, put a little more. When it says 14.01 grams, that means there are 6.022 times 10 to the 23rd in atoms on the scale. Nitrogen would be a gas though, so that's not a big step. I should have done carbon. And even though that's true, the 6.02 times 10 to the 23rd, it just doesn't show up when we use this type of statistics. So now I'm about to start going into some of these types of calculations. I think I can do it. But that's not a calculation. That's a statistic off the periodic table, which you don't have to memorize. You get a periodic table for everything. All right. Let's go on with this. So just pointing out what you see on the periodic table. I wrote it out as C atoms. We could just put C in quotation marks. But it's the same idea. You've got numerical value, grams, label, numerical value, moles, label. All right. So now, if I have 1.5 moles of carbon atoms, how many grams of carbon atoms do I have? Now you'll see why I was pointing out that there's, in those earlier calculations on this PowerPoint, there's a spot where there should be units where there weren't any. Here, they're all there. 1.5 numerical value, moles, unit, carbon atoms, label. How many, pound sign, grams, G, carbon atoms, in quotation marks. So now there are no blanks. And you don't see the blanks in the way the question is phrased. So forget 6.022 times 10 to the 23rd, that's not going to show up. But since human beings now know, we have our definition of the mole, and we know how many grams 1 mole of carbon atoms weigh. You get that right off the periodic table, 12.01. You look at your periodic table, you grab that, you line it up so moles will cancel. Moles of C atoms will cancel moles of C atoms. The label always goes with the unit. And that'll force you to end up in grams of C atoms, and that's it. That's how you calculate it. And again, notice there's no 6.022 times 10 to the 23rd anywhere here. Once we've got the periodic table and our grams per mole, we just get completely around those gigantic numbers and we just deal in grams per mole. So of course you finish this out, it's 1.5 times 12.011. We'll need to be in 2 significant figures. Comes down to 18 grams. If someone said, get me 18, somebody said, get me 1.5 moles of carbon atoms, I could sprinkle essentially graphite, but that's carbon atoms, onto the scale until it said 18, and I would have 1.5 moles to go give them. And this flips it around the other way, but still there's units everywhere. If I have 15.4 grams of carbon atoms, how many moles of carbon atoms do I have? So no more blank. You just set it, well, flip it, you set it up like that. In the top there, 15.4 grams of carbon atoms. Again, you could just put C in quotation marks. I don't know why I put atoms here. I did this as a presentation to somebody. I put those in. You make sure grams of C atoms is on bottom. So when you look at the periodic table, this is all you see, 12.011. But the rest of this is implied. The 12.011 is the grams. It's always on the scale of 1 mole. Anyway, calculate that out. 15.4 divided by 12.01. You get 1.3. That's the wrong significant figures. So whoever I showed this to, I don't know if they caught that or not. One, 2, 8. Oh no. I'm not sure what else. Oh yeah, okay. This is kind of the final point. Getting back to molecules. So too many transitions on my slide here, but you look at the periodic table, you can get the grams per mole for hydrogen, carbon, and oxygen. And very cute, very cute. Too much transition. All right. So this is the sort of punchline for today. Here's a molecule, C3H8O2. I think the only thing I want to do on the board, C3H8O2, that implies this. H8, 1, 2. guess I have to do. Just to give you an idea, that's the molecule that C3H8O2 is referring to. But we don't even really need that. Just reminding you, that's the formula for a molecule, C3H8O2. All right, what are the grams per mole for that molecule? So these are the numbers I got off the periodic table. I looked at carbon, 12.011, hydrogen said 1.008, oxygen said 15.999. Okay, we've got 3 carbons, 8 hydrogens, and 2 oxygens. So I'm going to multiply this one by 3. Many transitions. So I've got 3 carbons, 8 hydrogens, and 2 oxygens. If I multiply across, this is what I get. Then I add those up. And the sum of 36, 8, 31 and change is 76.065 grams per mole. That's the grams per mole for this. So we don't, since we have the grams per mole for every atom on the periodic table, we can figure out the grams per mole for any molecule that you could come up with. The formula for the molecule tells you how many of each atom is there, and then you just scale each one of those up to however many you need. So you can get grams per mole for every molecule that exists as well. Does that make sense? And then, of course, the final point, I guess if you wrote it, you could write it like this, but really, I don't know why I was being so pedantic when I made this. Usually when we're doing this, we just do the formula for the molecule itself and the quotation marks for the label. That's really a better way to do it. Hopefully I have a problem at the end. There we go. All right. Save that. So now if you have this problem, if I have 1.8 moles of C3H8O2, how many grams of C3H8O2 do I have? So you would have to go through the exercise we just did before. You can't get that straight off the periodic table, but you use the periodic table to come up with that, this, and the square here. So now you've got your relationship grams per mole for that particular type of molecule. Right. So, and you set it up the same way like I was doing before. You got 1.8 moles of C3H8O2. You're being asked for a number of grams of C3H8O2. And then you got that relationship that we calculated on the other page. Make sure you line up the moles so they cancel. You'll end up in grams, and that's how you do these types of calculations. You with me? So those units cancel. You crunch the numbers, and I did the significant figures correctly there. I guess I flipped this one over where I go. Notice on this one, go back to the start of this one. It tells you how many moles and it asks you how many grams. The next one I give you grams and ask for how many moles. Now I have 108.8 grams of this. How many moles of that do I have? And again, notice there's a unit for each numerical value. So you're not going to use 6.022 times 10 to the 23rd anywhere. But you set it up the same way, and you're going to use, well, you don't set it up the same way. This time you've got grams on the left and moles on the right. And of course, you're going to flip that over, so grams cancel. You with me? So I will upload this. Just keep in mind those powers of 10 are gonna revert back to not being superscripts like they should be. 4 significant figures, good. Save. And that's what I have. So for the rest of this, the rest of the practice problems I've made for you. What is the formula weight of KCl? Oh, yeah. I didn't mention this. I went ahead and put these in here, the ones that say AMU. But numerically, AMU is the exact same thing as grams per mole. So don't let AMU throw you off. We had what did we have? This is known as the molar mass. If I did it in AMU, different unit. So it's numerically the same, just don't worry about AMU. Anywhere you see AMU for anything we're doing, cross it off and say grams per mole and move on. There's a little bit of mathematical trickery to get it to be that way. And so anyway, so here you would look up potassium on the periodic table, get its grams per mole. Look up Cl, get its grams per mole. There's only one of each of those, so you just add them together, and that's what the numerical value is here. Cl is 35 and change. K is 39 and change. What's 39 plus 35? 74 and change, so the answer here is going to be this one. Don't ignore the change. What's after the decimal? I just did that quick in my head. This one, you have a cobalt and you have 3 NO3s. So kind of the quick way to do this when you have something in parentheses, 3 times 3 is 9, so you have 9 oxygens, and 3 times 1 is 3, so you have 3 nitrogens. So if you just remember how these ionic formulas work, you can calculate that. This one is going to be 21 times the number on the periodic table for carbon, and then 30 times the number on the periodic table for hydrogen, and 5 times the number on the periodic table for oxygen. Then you add those 3 results together, that's what's going to be here. All right. This one you just add everything up. So this is going to be 1, 2, 3, 4 carbons. So the formula there is C4, and then next would be H, 1, 2, 3, 4, 5, 6, 7, H8. N, there's only one N, O4. I think y'all can figure that out though. All right. Let's see. I'm going to stretch into one more description, but we won't do any math on it. So I'll go back here. So I said we were starting at 5.5, we're going 5.5, 5.6, and we've done those, even though I didn't use the chapter for it. Let me just circle back to introducing chemical reactions and balancing chemical equations, and just, I don't tend to make y'all balance chemical equations. But knowing what they are and how to use them, I guess we could use this one. Is that balanced? All right. So I'll write this up here. This is about where this usually goes out. Y'all watch where it says stop taking video, and if that changes, tell me. Because for some reason, we tend to get right at 1 hour and then it cuts off. Let me write this up. C6H12O6. This is called the chemical equation, and it tells you the chemical reaction that's taking place. CO2, 6 CO2 and 6 H2O. So the numbers out in front are called coefficients. I guess that's balanced. So these are reactants, these are the products. The arrow implies a chemical change. So you have this big molecule with carbons, hydrogens, and oxygens, and you get it to react with some oxygen. This molecule, the bonds literally break and reform and make a bunch of these molecules. That's what that's showing you. It is way bigger than I want to draw. Oh, that's 12. Here's 6. OH. Six of those. 2, 3, 4. O to H. I think I did that right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 of those. So let me just put a double bond here. I'm kind of ignoring the details here, but all right, let's say that's this big molecule. O2 is that. CO2 is that. And H2O, I'll draw it like that. That 6 is telling you you have 6 of these. Should have chosen something small since I only had 15 minutes. That 6 is telling you you have 6 of these. That 6 says we have 6 of these. And again, in chemistry, we drop the 1 when it's a 1, so there's only 1 of these. And the whole point is, between here and here, you have to have complete molecules, and no new atoms are added or taken away, meaning every oxygen that's over here, there's an oxygen for it over here. Every carbon that's over here, there's a carbon for it over here. Every hydrogen that's over here, there's a hydrogen for it over here. That's what these coefficients are ensuring. And there is a 1 here. 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6 carbons. Oxygens, there's 6 oxygens in here, if I did it right.
6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So there have to be 18 oxygens over there. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Yep, so far so good. We have 12 hydrogens here, if I drew it right. 2, 4, 6, 8, 10, 12. That's it. That means this equation is balanced. You have to balance an equation for it to be useful for anything. But like I said, I shy away from making you guys balance these. I just drew all this to tell you what this means, what it represents, physically what it represents. What you want from this, yes. So let's say you had that in front of you. I didn't make you balance it. In the same sense that grams per mole is a relationship of number of grams to 1 mole for any individual atom. We can have grams per moles for these. Here's some relationships for this particular reaction. Really, this reaction, there are 6 relationships there that it's giving you. And you usually only need one of these relationships when you're using something like this. But when this reaction occurs, for every 1 mole of this, it takes 6 moles of this. That's what this says. That's one of the relationships. The next relationship, I'll do these two. I did these two, now I'm going to do these two. 1 mole C6 H12O6 to 6 moles CO2. That's telling you for every 1 mole of these that react, you will get 6 moles of CO2. I've done these two, I've done these two, now these two. To 6. Usually you don't have the same repeating number over and over. But that's saying for every 1 mole of these, you'll get 6 moles of H2O. You with me? And now the rest of these, there's these two I can do, and these two, and these two. And yeah, you might look at that and go, okay, write the next one, Embry. 6 moles of O2. So I'm relating these two. So for every 6 moles of these, after the reaction, we'll have 6 moles of these. Yeah, you could just do it 1. You could cancel the 6s. But that's the idea. And there's 2 more. There's what do I do? These 2. So there's those 2 that I can still write, and these 2 I can still write. There's 6 relationships buried, summarized in that chemical equation. That's the key to the way I'd have you use it. If I just gave it to you already balanced, there's things you can calculate. So given a question, if I put X number of moles of this in, how many moles of this will I get? You're going to use your setup, one of these is your relationship, then equal sign, then the answer. But I'll start there next time. But do go through these. I don't have any questions on these. I just wanted to introduce it. That's where we'll start Thursday. Practice those that I put up there. Practice those calculations. Man, it's hot here today. It's not just me, right?